What is buffering? Buffer and buffering are terms that are thrown around indiscriminately in the world of reef keeping, and the actual meaning of these terms is often lost. Many aquarists refer to any alkalinity supplement as a buffer, but this isn't the case. For example, neither sodium bicarbonate nor sodium carbonate taken alone is a true buffer. A buffer is something that helps minimize pH changes in the presence of added acid or base. No buffer can completely stop the pH from changing when acid or base is added. The change in pH, however, is made smaller when an appropriate buffer is used. A buffer is almost always comprised of two different chemical entities. Bicarbonate and carbonate together, for example, form a buffer in the pH range from about 8 to 11 in seawater, though the buffering is best between about 8.5 and 10.0, ignoring that at high pH some calcium carbonate may precipitate. Okay, so when we talk about buffer is something that help minimize pH change. Okay. Here's what is happening on a chemical level. When a base such as OH minus is added to the system in an effort to rise pH, some of the bicarbonate is converted to carbonate. This process effectively uses up some of the OH minus that was added, and the pH does not rise as much as it would without the buffer. So we have bicarbonate reacting with base, it becomes carbonate to form carbonate. So overall we have bicarbonate and carbonate plus base, which result in less bicarbonate and more carbonate. Carbonate, yes. When an acid H plus is added to the system in an effort to lower pH, some of the carbonate is converted to bicarbonate. This process effectively uses up some of the H plus that was added, and the pH does not drop as much as it would without the buffer. Carbonate plus acid equal more bicarbonate. So overall we have bicarbonate, carbonate plus acid will be more bicarbonate and less carbonate. Of course, in order for this process to buffer against both pH rises and pH drops, there must be a significant amount of both bicarbonate and carbonate present. At about pH 8.9 in seawater at 25 degrees Celsius, there are equal concentration of bicarbonate and carbonate. Okay, so equal concentration. At lower pH, there is less carbonate, and at pH 8.0, there is really quite little carbonate in seawater, only about 4% of bicarbonate level. Consequently, seawater is not especially well buffered against substantial pH drops when the pH is already less than 8.0. It is, however, well buffered against substantial pH rise. Here's an example. Here's an experiment. Take artificial seawater in solution as S35, alkalinity measured to be 2.26 MeQ per liter by titration, and add 0.5 MeQ per liter of either acid or base. The results of an immediate pH measurement before atmospheric carbon dioxide has a chance to equilibrate are: starting solution pH is 8.10, sorry. So adding 0.5 MeQ per liter of base, it increases to 8.76. Adding 0.5 MeQ per liter of acid, pH drops to 6.91. So as we can see, the added base OH minus drives the pH up by only 0.66 units. Yes, while the added acid dropped the pH by 1.19 units. This result shows that the water is better buffered against a pH rise than a pH drop. And the reason for this difference is simply that there is more bicarbonate than carbonate and pH 8.1. The only reason that the drop stops at pH 6.9 is that at that point, bicarbonate is really doing the buffering as it is converted into carbonic acid. The difference in the buffering against substantial pH rises and drops is obvious from such an experiment. Nevertheless, there is much more to fully understanding how a buffer works. Chemists have chosen the term buffer intensity, symbolized by B, to reflect the buffering capacity of a solution at any given pH. While it has an exact mathematical definition, it is beyond the scope of this article to describe B in detail. There are, however, a few details worth mentioning in the context of reef keeping. Detail provided. Okay. The most important fact to reef keepers is that the buffering due to bicarbonate and carbonate at a given pH is directly related to the carbonate alkalinity. If you double the alkalinity, you double B, and hence have twice as much buffering due to the carbonate and bicarbonate system. In normal seawater, the carbonate-bicarbonate system provides a substantial portion of the total buffering, which is quantified below. Consequently, marine aquaria with higher alkalinity tend to have greater buffering against pH swing. Other, more esoteric tidbits arise from this system as well. For example, while the buffering against substantial changes can be different in two different directions, as shown as experimentally above, which is this, the buffering against very small changes is necessarily exactly the same. That's what B represents. The buffering against infinitesimally small changes in pH in either direction. B changes as a function of pH, and maximal when the concentration of the two forms of the buffer, example bicarbonate and carbonate, are equal. In seawater, B is locally maximized around pH 5.8, where the buffer is carbonic acid bicarbonate, and at is locally maximized around and at a pH 8.9 where the buffer is, ignoring the fact that other things happen at high pH like precipitation of magnesium hydroxide, and calcium carbonate. These are the points where seawater is most resistant to changes in pH as acid or base is added. Unfortunately, reef tanks are not usually kept at those pH values, and so the buffering effect of the carbonate system is not as effective as holding pH steady as it might otherwise be. This lack of effective buffering at a normal tank pH is one of the reasons that some salt manufacturer, CCAM, boost the borate concentration in their salt mix. Since the pKa of borate in seawater is about 8.6, its maximal B pH 8.6 is not far from the range experienced by reef tanks. In normal seawater at pH 8, borate provides about half of the buffering against a small downward pH change, despite the fact that it provides less than 3% of the total alkalinity. In CCAM salt, where borate is about 10 times natural levels, borate totally dominates the buffering in the pH range experienced by reef tanks.